All right, gang. Stat 1800. I got to tell you right now, I'm not feeling the greatest today, so I don't know how this is going to go. We'll see. Time will tell. If it gets too bad, then I'll scratch the videos, and you'll never know anyway. So I don't guess it's that big of a deal. All right, gang. Moving into new stuff, and we're moving into where I think we're kind of moving into big boy, big girl statistics. What we've done so far is we've looked at hypothesis testing and confidence intervals for one sample. So today we're moving into comparing two samples. If I could write, it would be nice, right? So the kind of the sub goals here of where we're headed. We want to look at independent means. So compare two means that are independent. So two means from two different populations. More about that in just a second. The second thing we want to look at is we want to look at dependent means. So we have two samples, but the samples are collected on the one person. On one person. So imagine having like 20 people and you give them a pretest, and then you do some sort of intervention, and then you bring them back later and do a post-test. So you have the two measurements are on the same person. So that's why we call it dependent, because you do not have the independence assumption. For obvious reasons, you're measuring the same person twice. Independent means are two different populations. So we might want to investigate the ACT scores at Shawnee State University across males and females. So we would expect those to be independent, because you wouldn't think that someone's ACT in the males would in any way, shape, form, or fashion impact or be related to the ACT for males. The other one we're going to look at is two proportions. What two proportions again kind of falls under the independent. Well, it definitely falls under the independent realm. So if we wanted to know the percentage of people who intend to vote, for example, for Donald Trump in the next election, I'm assuming he will run. And we're wanting to look at that maybe across Kentucky and Ohio. We could compare the two proportions using this procedure that I am going to teach you. All right, gang. The beauty of moving into two sample t-test or two sample test, hypothesis test, is if we have a good foundation, which we should, especially if you've been watching the videos and submitting the assignments, we have a good foundation on hypothesis testing in general. So, that said, one of the first places we start is, what distribution do we use? And right now, the two distributions we have are Z or T. Now, there's another distribution called F distribution that we get into a little later. Remember Z, mean is 0, standard deviation is 1, and the T distribution relies on the degrees of freedom. And a lot of times students will ask me, well, how do I know whether it's the Z or the T? Well, that's my job, is to teach you that. Remember, if we have a population standard deviation known or a one prop hypothesis test, it's a Z test. But if we have a claim about a mean where the population standard deviation isn't known, well, that's the T distribution. The next thing we do is we state H sub O and H sub A, or as your book likes to do it, drives me crazy, but I'm trying, or H sub O or H sub 1. The next thing we do is we calculate the test statistic, and we calculate the p-value based on the distribution that we know we're using to model the problem. Final thing we do is we make our decision, reject or fail to reject the null. And then finally, we usually want to come in and calculate a confidence interval. Now, gang, let me take this back up to the test statistic. The test statistic, whether we have a T or a Z stat, always follows the same general form. We have a value minus a value divided by a value. And the secret to being able to calculate a test statistic, which is used to calculate the p-value, which is ultimately used to make your decision, is knowing about these three components. Now guys, what usually goes here, if we're going to look at, for example, let's say we're conducting a test of hypothesis for a mean, then we're going to have the sample mean right there. We're going to have the value of mu that's being tested in H sub O, and then we're going to have our standard error, which is Sx over the square root of n, if the population standard deviation is unknown. So guys, what goes in this part right here, that's the sample statistic. This is the claim in H sub O, and this part right here is the standard error. Okay? Now, what does all this look like in a independent samples t-test? What does this look like? Now, first of all, let's get a pretty thorough understanding of the dynamics of what's going on here. So imagine we've got some population, and we'll just call that mu sub 1. So this is a population number 1. And this population has a mean. Of course, the mean's unknown because usually populations are extremely large, and the population means are typically unknown. Now, let's say we have a population number 2. It also has a mean, so we'll let it be mu sub 2, indicating that it comes from population number 2. All right? So we wonder, is there any difference in these two means? So we would start out with our H sub O, and we would just assume that the two means are equal. Now guys, a little bit of algebra, you can see if we subtract mu sub 2 on both sides, mu sub 2 minus mu sub 2 would give us 0, and then if we subtract mu sub 2 over here, we get mu 1 minus mu 2. So this is equivalent to saying if the means are different, if the means are the same, then the difference in the means has to be equal to 0. Makes sense. 5 equals 5, right? 5 minus 5 is 0. So again, this is our H sub O. The H sub A, I'm going to go with 1 just to make the author happy, I guess. We would assume that these two are not equal to one another. And guys, this is equivalent to saying that the difference kind of hard to see, is not equal to 0. Now the same thing, we can come in still, if we want to do a directional test, we could come in and do, less than or equal to and greater than. So we can, we can do, well, that would be less than or equal to here. But we'll get examples of that, I think, in a couple of videos. But right now, we're just going to look at a two-tailed test. So what we do is we dive into this population right here, and we take a sample. And that sample ends up having a sample mean. We'll call that x sub bar 1. It has a standard deviation, so I'll call that S sub x1, meaning that this is a sample standard deviation that was collected from that population. N sub 1 is the sample size, and we're going to have the same information over here. X bar sub 2 would be the sample mean that we would collect from this population. Sx sub 2 would be the sample standard deviation from that population, and N sub 2 would be the sample size of the sample that we took from this population. Now, let's move on into the test statistic. Now, these types of problems are modeled by the t-distribution. So we don't need to use the Z distribution here unless unless the population standard deviations would be known. And I'm not going to cover those types of problems in this class because they're so rare, and most of the technology doesn't even cover that anyway. So again, the test statistic is 3 parts. It's the sample statistic, it's what we get in H sub O, and it's our standard error. Now, since we're evaluating whether or not mu1 is equal to mu2, specifically whether mu1 minus mu2 is equal to 0, it should make sense to you that the sample statistic is the difference in the 2 sample means. It should make sense to you that we look at the difference in our sample to estimate the difference in the population. Now, the null hypothesis, what happens here, this difference is assumed to be equal to 0. So that's kind of redundant because that's ultimately all just going to collapse to be just x bar 1 minus x bar 2. Now, unfortunately, the standard error turns out to be kind of goofy and kind of wacky. The standard error is the square root of the pooled variation times 1 over n1 plus 1 over n2. And again, n1 and n2 are just the sample sizes of the 2 samples we drew from each of these populations to examine the difference in the population means. Now, this pooled variance, this S squared P, now it's not crazy to calculate, but it's I don't know, it's maybe a little bit crazy. Okay, so the pooled variance is just well, let me see if I can remember this. N1 minus 1 times the variance of the first sample plus N2 minus 1 times the variance of the second sample. And then the numerator is just N1 plus N2 minus 2. And, you know, it turns out that this distribution that models this, of course, is the T distribution. And the degrees of freedom for this distribution are N1 plus N2 minus 2. All right, guys, I think we've got the kind of the foundation set. You know, we'll follow the T distribution, and if we're doing a 2 sample, we'll have a T critical and a T critical. And this will be for the you know, the alpha over 2. So if we have an alpha 0.05, we put half of our rejection region here and half of our rejection region here. All right. So guys, the beauty of this stuff is that when we start doing the calculations, we actually will do most of that using StatCrunch. So guys, I'm going to keep this this video short. And the next video, what we'll do is we'll run through a test, a 2 sample test using some data, and I'll show you how all this stuff works out. So guys, have a good one.